Okay, so one of the coolest ways of seeing how these kind of excitonic models, sometimes also called tight binding models, are useful for molecular structure. And since we'll be able to get something out that tells us a little bit about the electronic structure, at least for a subset of the electrons, it'll also give us some energy level diagrams, and those are ostensibly one of the goals of the course, is to be able to show a link between structure and spectrum. That's not always so clear, but we'll start. Okay, so as I've said before, and I hope someone has said it to you before as well, most of the color that we see, if we see color, is due to transitions between electronic states in conjugated molecules. Conjugated molecules are molecules that have alternating single and double bonds. The more conjugation you have, the larger the electronic delocalization, and the closer together will be the energy gaps, just like in a particle in a box. And so that would make the material absorb longer and longer wavelength and then look like the complementary color, whatever is not being absorbed. Here's an example of 1,3,5-hexatriene. Of course, there's many other examples you can conceive of. Here's an example. And there are lots of molecules like this. The ones that are absorbing sort of in the middle of the visible for plants are called carotenoids. You've seen carrots and broccoli and other vegetables. The ones that absorb in the bluish part of the spectrum, and in the other reddish part of the spectrum might be from chlorophyll, and those are rings with the metal in the middle. Right, so there's many, many examples. Your molecule in your eye right now that's letting you see all of this is a protein called rhodopsin. In the middle of it has a conjugated retinol chromophore, which absorbs light, isomerizes by a photochemical reaction, and then causes a rather complicated cascade of signaling to polarize your retina and start a neuronal response. All right, so these are really common, and so although it might seem like we're only developing something that's useful for a particularly special case, it's a special case that's actually really useful, right? So that's why people do this. All right, so what we're going to do is we're going to go back to what we talked about before when we mentioned the particle in the box motivation at the beginning, and that is, you have these structures of these molecules. As I've drawn them, they probably would lie flat on the surface of the board, at least if the temperature's reasonably low. And the reason for that is because the main structure of the molecule can be kind of described as combinations of s and p orbitals, sometimes called sp2 hybridization. Now, when we do quantum chemistry, there's no sp2 hybridization in there. It just uses a different basis. sp2 is a basis just like anything else, but it's a basis that gets you pretty close to the answer right away. So that's why it's a concept, I think, that has persisted in the organic community, even though even organic chemists don't use hybridization when they do quantum chemistry either. They still put the same Gaussian orbitals on their atoms like we do. All right, nevertheless, it seems like a conceptual framework, and what ends up happening is there's obviously a kernel of truth in it, because what you end up with, once you take care of making this sort of sigma structure, the structure that's everything in that plane, you're left with the p orbital on every single one of the carbons that is contributing to this conjugation. So on each atom site, you're going to have a p orbital that's sticking out of the board, right? And for the non-chemists, we draw the structures typically with organic molecules. We just ignore it. We delete or do not put in the hydrogen atoms. So everywhere you would have a carbon here, and then it would be 1, 2 bonds, 3. There would be a hydrogen here. There would be 2 hydrogens here, and so on. We omit the hydrogens. All right, so there's really 4 things, or 4 bonds, if you will, to each carbon. So sometimes it's single, sometimes it's double, and when you have the ring, we're just indicating that there can be different structures that also give you this alternating single-double bond inside these so-called aromatic groups here. Now, all this issue of aromatics and stuff, it will pop out automatically from Hückel theory, which is pretty cool. All right, so what do we do? what we do is we look edge on. Let's do it for hexatriene. That's sort of an easy place to start. And we're going to imagine having each of the carbon atoms, which I will put in blue here. 1, 2. Those are the sites. When I'm going to use the term site. The reason I'm using the word site is because later on, when we realize this is a general thing that applies to a lot of stuff besides Hückel molecular orbitals, this is going to be, each site might be a different vibrational mode, or it might be a different whole molecule if we're coupling together molecules. All right, and what we're going to do is we're going to imagine that there's one of these unhybridized, so to speak, p orbitals on each one of the hydrogens. Right, and we're going to basically model the p orbital like a two-level system on each carbon atom. Okay, and the way this works, it's actually pretty straightforward. What we're going to do is we're going to have a certain energy of exciting or occupying or having a p orbital being a plus sign and a certain sign. Then what we're going to do is we're going to imagine making a two-level system that's coupled together. The coupling in the Hückel theory will come from the adjacency. Now it actually matters where they are physically in space. So we're going to have a certain energy of excitation above the ground state, which is called alpha, okay, which is essentially just the energy of thinking of energy of the p orbital. And then what we're going to do is we're going to have a coupling between them. And to make the model as crude as possible, we are not going to change the coupling ever. We're just going to pick one number. That's the coupling parameter, which is called beta. Right? It turns out beta is negative for this. All right? So assuming what we then do usually is set alpha equal to 0. So we set the energy of this excited state equal to 0. Right? And then that will cause the system to split up and down according to this coupling pattern. But we don't have to do that. We can leave it in terms of alpha. You saw before, I could have made the ground state, instead of making the ground state 0, I could have made the ground state minus epsilon, made the first excited state epsilon, or 0, and then the second excited state could have been epsilon plus epsilon. The two levels would have split. Everything would have been exactly the same. Okay, so what we do then is we imagine we have a site energy for each of these things, and we have a coupling between them. All right? And let's see what that means. So what that means for this is we make a Hamiltonian that looks like alpha on the diagonal. How many elements are going to be? There are going to be 6 elements. 2, 3, 6. All right, so that's the site 1, 2, 3, 4, 5, 6. 1, 2, 4, 5, and 6. All right, and then what we do is we simply put onto the diagonal the energy of exciting one of these, or sort of being in one of them, and that's going to be alpha. And now comes the chemistry part, the connectivity. So we know that 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, and so on, but 6 is not connected to 1. Okay, so inside every place where we have a connection, so 1, 2, for example, we put beta. I can even use a different color. Beta. The matrix has to be symmetrical so that it's Hermitian. And we keep doing 3 and 2 are connected. 3 and 4, so 2 and 3, 3 and 4, 4 and 5, 5 and 6, and then symmetrical. Everywhere else is 0, so we can just omit the zeros. That's it. One number, 2 numbers, I guess, if you will, because the alpha number we can figure out. And then we have one coupling parameter, and we're not changing it. We're not making it different because they're on the edges, for example. You'll see you don't need to. You will still get something that looks remarkably similar to the full-blown, high-end 21st century quantum chemistry result by using this ancient technology. All right, so what do we have to do? We have to do the eigenvalues and the eigenvectors again. Okay, and so what I've done is I have a simple MATLAB program that calculates this and then plots them. Now, how does it plot them? What it does is it will plot the eigenvectors, right? So, for example, the lowest energy eigenvector, which we could call, I don't know what I want to call it, epsilon, the eigenvector with energy epsilon 1. Remember, this is going to have elements in it, 6 of them, that tell me what amount of each of these p orbitals I'm adding together into my overall eigenfunction that corresponds, or eigenvector that corresponds to an eigenvector of this Hamiltonian with the lowest value of energy. And what you're going to find is, so what we're going to plot is the magnitude of each eigenvector element, right, versus the site location. So 1, 2, 3, 4, 5, and 6. Okay, and there'll be the magnitude. You can plot the magnitude squared, or the. I think in this case they're all real, so I just plot the magnitude, so you can see the sign. And that's kind of interesting. All right, and what you're going to see, I'm going to show real results over here, but let me walk you through it first. What you're going to see are little bar graphs. That look like this for the grounds, for the lowest energy one, which is to say that you have some amplitude on each of the p orbitals, some occupation of each of the p orbitals with a particular sign that's all positive here. And what we want to compare this to is what we remember from the particle in the box, which is at the ground state wave function, or a ground state eigenfunction. Looks like this. Okay, so that's what you're going to see for epsilon 1. For epsilon number 2, epsilon energy, the first excited state, what you're going to see is something a little bit different, right? What you're going to see is, I don't know exactly the shape, that's why I do it on the computer. You're going to see that there's a sign change between them. Something like this. Now, of course, you could just look at the numbers if you want. But you'll notice what's sort of interesting here is right in the middle of the molecule, you have this node, right? And of course, this node resembles the first excited state of the particle in the box. Well, that automatically comes out when you do this Hamiltonian. Okay? And you'll see the results here. So now the results are being shown, and you can see all 6 of those eigenvectors. Okay? And then they have energies also associated with them. All right. And those tell you something about the energy. Now, the energies are very crude. In principle, what you would do is you would try to adjust the values of alpha and beta to get you something that might correspond to some actual experimental results, or maybe some theoretical results. You could also say, well, I know I can calculate this molecule, no problem with quantum chemistry, and I can figure out what the energy levels of the states are, the eigenstates are, when I do it that way. And maybe there's a way to find an optimal setting for beta and alpha that gets me those energies, right? We're not trying to get accuracy. We're trying to get insight. The numbers are whatever the numbers are. The question is, can you get a physical representation of a molecular orbital by simply imagining you have 2-level systems that are coupled together that represent the p orbital? And the answer is you can. Now, what else can you get from this? Just to make sure that it's very clear how useful this is. What if I change it from being 1,3,5 hexatriene? What if I turn it into benzene? Okay, to turn it into benzene, it turns out I don't have to do all that much, do I? Right? I have carbon 1, 2, 3, 4, 5, and 6. Everything is the same except one thing, right? What's the one difference? Now all of a sudden I have a connection between 1 and 6 that I didn't have before. All right, so in that element, we put a beta. That single act of putting the beta in these upper right and bottom left off diagonal element is enough to change the energy level structure and the symmetry of these eigenstates to reflect what you expect to see in a molecule like benzene. Right? If we look at the ground state, the lowest energy, so if we look at the similar kind of representation, what I think most chemists expect is that you have an equal distribution of electron density in this pi system around the ring. That's the reason we draw the circle here. And that's exactly what you get from this. You get the same amplitude on all 6 of the sites. And that comes simply from the fact this is for epsilon 1 in the case of benzene. And of course, this is 1, 3, 5 hexatriene. All right, rather than try to draw them all, I'm going to show you now the eigenvectors in the same kind of bar graph for benzene. All right, and as you can see, the bar graphs that we get are very reminiscent, if not very almost perfect representations of what you get when you do the whole thing with proper quantum chemistry. And that's what I'm showing at the same time. So on one side, you're seeing the Hückel theory result, and on the other side, you're seeing the molecular orbital theory result, just using Spartan and a basis and DFT and so on, like we've discussed. Right? So you can see those orbitals. Not only do you see that, what's the main, one of the things that you see in the benzene case by simply adding these 2 elements here? You find there's degeneracy, right? Because you expect degeneracy in a two-dimensional system like this that's symmetric. And because of the symmetry, there should be some degeneracy. And that's exactly what you find. And the degeneracy pattern matches perfectly the pattern that you see when you do it with proper quantum chemistry. And in fact, that degeneracy is part of the reason why the benzene molecule itself is so stable. And that allows it to resist reactions. Of course, you can do reactions on these, but they're pretty inert. Once you've broken the symmetry by adding something, for example, like making it into toluene, then all of a sudden chemistry is different, and there's different kinds of chemistry, and you know where each part of the molecule is more likely to be attacked chemically in a chemical reaction, depending on what the group is here. All right, and so the idea is, of course, that chemistry has to be somehow included in the quantum mechanics, not necessarily in the Hückel theory. But if you imagine tweaking this model a tiny bit, what you might do is you might say, well, I have a methyl group here. Right? Methyl groups are what chemists call electron donating. So they add electron density in this direction. So one option you might do is you might just say, well, let's change the alpha parameter for the carbon that has a methyl group on it. That's going to break a little bit the symmetry. And then you might say, oh, okay, does that make some electron density grow somewhere else? And I might be able to determine about, say, ortho, para, and meta-directing groups, just from a simple model like this. And of course, this was worked out decades ago, but most people forget all this stuff, because I guess maybe it's easier to just to do it in DFT and not learn these extremely simple models. All right, so what we have then, this whole thing is called Hückel theory. And you can still use it. I mean, the quantum chemistry programs use this. Probably a lot of them will get started using something like Hückel theory at the very beginning of a more complicated quantum chemistry run that you would do. But for my purposes, the main thing is to show you how this very simple picture can give you some power. Now, a couple of things I'm not going to talk about, but if you're interested in this, there are ways of calculating from Hückel theory, for example, the aromaticity, finding out that 1, 3, 5, 7 octatetraene, for example, might be different from benzene or whatever. So you can have aromaticity, anti-aromaticity. You can treat things like cyclopentadienyl ligands. The way this works is this thing has a formal charge of minus. So by a minus, all I have to do is add another electron. Okay, that makes it aromatic. Whereas if you don't have the extra electron, it's not. It's bent here. All right, so the ideas of aromaticity, the stabilization caused by the delocalization, all that actually can be analyzed by looking at the eigenvectors of the Hückel Hamiltonian that you have. Not only that, it allows arbitrarily complicated molecules, right? How do you make this one? You just number all the carbons, starting, for example, I have no idea what the official place to start is, so let's just start here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You make a 14 by 14 matrix. You find all the places where they're connected by conjugation, put a beta there, put alphas on the diagonals, put 0 everywhere else, flip the switch on your MATLAB, and get out the eigenvectors and eigenvalues of this. Keeping in mind that visualizing it's a little bit trickier, you'll have to have some kind of occupation. But I think I made a program once, and I'll try to dig it up, which actually takes like a structure of a molecule and then draws little circles of different sizes to reflect the magnitudes of these, and then changes the color to be the sign, like red and blue, to be positive and negative. And then you can see right on the picture something that looks like, obviously, like a kind of a cartoon representation of what you would find if you did like a proper, fancy calculation using quantum chemistry with all the bells and whistles of DFT or whatever in a basis set that's complicated. All right, so this is the Hückel. The next example I'm going to do, which shows you how coupled two-level systems can be extremely useful, is to understand coupled vibrations as well as anharmonic coupling in molecules, which is very important for infrared spectroscopy. And that will be the next bit on this.